So here we are at Kaggle's Intermediate Machine Learning XGBoost. So this is the most accurate modeling technique for structured data. Before we get started, a couple nights ago, or maybe it was last night, I can't remember, I actually had a dream about machine learning. And you know what? I got the MAE down. I got the MAE down to like 832 in my dream. The only part of the dream I don't remember is how I did it. It is what it is. But you know what? And I'm a little bit more before we go into it. One of the things is whenever I used to like work at really crappy jobs, right? The second I had, the night I had a work dream, like when I was a waiter in my youth, and I would have a work dream, a dream about work. It was about the beginning of the end right there. I would definitely be quitting maybe a week, maybe 2 weeks after having that dream, because you know what? I refuse to go to a job that I hate and then dream about it too, as if I have no escape from it. But this is different because I want to do this. So there we go. In this tutorial, we're going to learn how to build and optimize models with gradient boosting. This method dominates many Kaggle competitions and achieves state-of-the-art results on a variety of datasets. Here's the introduction. For much of this course, we've made predictions with the random forest method. Yes, which achieves better performance than a single decision tree simply by averaging the predictions of many decision trees. Yes, we went over this in the beginning. We refer to the random forest method as an ensemble method, believe it or not. By definition, ensemble methods combine the predictions of several models. For example, several trees in the case of random forests. Okay. Next, we're going to learn about another ensemble method called gradient boosting. All right. So gradient boosting is a method that goes through cycles to iteratively add models into an ensemble. It begins by initializing the ensemble with a single model, whose predictions can be pretty naive. Even if its predictions are wildly inaccurate, subsequent additions to the ensemble will address those errors. All right, another thing. There's going to be a lot of words in here and a lot of sentences that I have no idea what they're saying, like this one. But it is what it is. We're just going to keep going through. We'll figure it out later, right? We just got to keep pushing. So then we start the cycle after we do whatever this just said. First, we use the current ensemble to generate predictions for each observation in the data set. To make a prediction, we add the predictions from all models in the ensemble. Okay. These predictions are used to calculate a loss function like mean squared error, for instance, right? And if we click this, we can see we get a Wikipedia page. And you know what happens if we scroll down? Oh, buddy. Oh, buddy. Oh, wow. And then we get to the part that I've been trying to avoid, the math, or at least the calculus. But you know what? No big deal. No big deal. No big deal. Okay. We will know what this stuff means at some point. Today, we will just keep going. So then we use the loss function to fit a new model that will be added to the ensemble. Okay. Specifically, we determine model parameters so that adding this new model to the ensemble will reduce the loss. Here's a side note. The gradient in gradient boosting refers to the fact that we use gradient descent on the loss functions to determine the parameters in this new model. Let's click this, and we can see right here. If we scroll down on this Wikipedia page, here's gradient descent in 2D. Well, it looks pretty good, right? I mean, I like it. Anyway, that's a visualization. We can also look at math formulas if we want. Not that. Okay, and then here's an illustration of gradient descent. I mean, look, guys. This is the thing that we're dealing with in life now. Okay, as people that have gone and stepped square in this quicksand that is machine learning, this is what we have found when our heads went under. Okay, this is reality for us, and we're going to have to figure this stuff out. Barzai-Borwein method and all this stuff. We're going to have to figure all this stuff out, but not today. All right, finally, we add the new model to the ensemble, and voila, we're going to repeat. So basically what it's saying is we've got this naive model, which they were talking about up there, and then we're going to make predictions with it, calculate the loss, train the new model, add the new model to the ensemble, make predictions, and then keep going until we find the lowest MAE. All right? Basically. So here's an example. We begin by loading the training and validation data in xtrain, xvalid, ytrain, and yvalid. Okay? And here we go. We've got the stuff right there. It looks completely different than the other one. What's going on here? Why does it look like this? Whatever, I don't care. All right, pardon me. In this example, we're going to work with the XGBoost library. XGBoost stands for Extreme Gradient Boosting, which is an implementation of gradient boosting with several additional features focused on performance and speed. Okay. Scikit-learn has another version of gradient boosting, but XGBoost has some technical advantages. Let's do this. Something's up here. I don't like it. All right, cool. This is better. All right, so we were just right here. So in the next code cell, we import the scikit-learn API for XGBoost. All right, this XGBoost.xgb regressor, and this allows us to build and fit a model, just as we would in scikit-learn. As we'll see in the output, the XGB regressor class has many tunable parameters, and we will learn about those soon. Okay. So yeah, we're going to, from here, XGBoost, we're going to import the XGB regressor. We're going to say my model equals this XGB regressor class, and then we're going to do the my model.fit, and we're going to put xtrain, ytrain in, just like we normally do. Except, here's the hidden output. As you can see, we start with B, we got C, E, G, I, M, and it goes all the way to R, and then it has some ellipses. So basically, there's going to be a ton of different parameters that we can tune in this. And you can see right here that we've got the NM estimators equals 100 as our default. And we've got all kinds of stuff in there. So just letting you know on that. We're also going to make predictions and evaluate the model, right? So from sklearn.metrics, we're getting mean absolute error. And then we do predictions equals my model.predict xvalid. And we can see we're going to print mean absolute error with a colon, and then we're going to have the string for the mean absolute error at predictions at yvalid. Okay. With, anyway, you know how this works. And we see right here, it's just with nothing in it, with no tuning of these parameters. It gives us a pretty high MAE, but we can change that later. All right. So here's parameter tuning. XGBoost has a few parameters that can dramatically affect accuracy and training speed. The first parameters we should understand are in-estimators, like we saw up there, and in-estimators specifies how many times to go through the modeling cycle described above. This is equal to the number of models that we include in the ensemble, all right? So remember, in-estimators, when we were using it on the regression tree, was how many trees we have and how many trees it goes down. But in this one, in estimators, is how many times this thing spins around and around and around and around until it gets us some MAE, right? Some mean absolute error. So too low a value causes underfitting, as we could imagine, which leads to inaccurate predictions on both training data and test data. And then too high a value causes overfitting, which causes accurate predictions on training data, but inaccurate predictions on test data, which is what we care about. True. Absolutely true. We know that already. So the typical value range is from 100 to 1,000, though this depends a lot on the learning rate parameter discussed below. Yeah, we'll get to that, but I don't really understand it down there either. Here's the code to set the number of models in the ensemble. Okay, so we did this, and now we're setting the in-estimators to 500. And when we show the output, we can see down here, in-estimators is now 500 instead of 100, which was up there. And from here on out, it's just going to keep doing this thing over and over. So we're just going to skip the reading the output. And that's because we can just imagine what's going to actually happen. All right, so let's go. So now we've got early stopping rounds. Early stopping rounds offers a way to automatically find the ideal value for in estimators. Early stopping causes the model to stop iterating when the validation scores stop improving, even if we aren't at the hard stop for in estimators. So basically what this is going to do is stop it at the best one. So if it goes low, 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 and then it starts moving up, it's going to stop it. And that's very convenient. We're not going to have to deal with going through and trying to figure out which one is the best the best estimator to stop at. It's just going to do it for us. All right, and that's great. It's smart to set a high value for in estimators, like 1,000, and then use early stopping rounds to find the optimal time to stop iterating. True. Since random chance sometimes causes a single round where validation scores don't improve, we need to specify a number for how many rounds of straight deterioration to allow before stopping. So basically, sometimes when it's going down, it'll go back up for one and then start going back down again. So to stop it from early stopping on a little anomaly, we're going to do this. We're going to set the early stopping rounds to like 5. Okay. And this is a reasonable choice so that maybe it gets down to like, let's say it gets down to like 40, right? And then it says, okay, now it's 41, 42, 43, 44, 45. It knows now that it's not an anomaly and it actually was good enough at 40. But at the same time, I don't know if it's going to give us the 45 or if it's going to give us the 40. I don't know. We'll get to that later. In this case, we stop after 5 straight rounds of deteriorating validation scores. Excellent. So when using early stopping rounds, we also need to set aside some data for calculating the validation scores. And this is done by setting the set eval parameter. So instead of running validation separately, we're going to do it inside of the XGB regressor. We can modify the example above to include early stopping. Right. So in this one, we can see we're doing the in estimators 500, and then we're adding early stopping and eval set to the model fit. But the thing is, when we get to the exercise, we're actually going to be putting this inside of this because that's just how it is now. This is the old way and that's the new way. Okay. And it'll tell it, it will not be shy about telling us it's not going to work. Okay. But then we're going to do this. We're going to do the set. We're going to do the eval set right here with the X valid and Y valid. So we don't have to run an X valid and a Y valid on something else. All right. So it's just going to do that right here. Looking good. Verbose equals false. No idea. We'll figure that out later. All right. So there we go. If we later want to fit a model with all of our data, we're going to set in estimators to whatever value we found to be optimal when we ran it with early stopping. The thing about that is I also don't know how to find out what the good in estimator was. We'll have to figure that out later. Probably Jim and I will tell us. But right now, they're not telling us. All right. And remember, guys, we're at advanced learning now. So these guys aren't going to tell us everything. They're pretty much going to hang us out to dry. All right. It's like that. But you have to also understand, at least these guys aren't bums like those guys on Free Code Camp that tell us to donate money after every single lesson. You know what I'm saying? So at least they got that going for us. So we can definitely, absolutely forgive them for hanging us out to dry because at least they're giving us this much, right? Without saying, hey, give me money. You know what I'm saying? Anyway, let's go. So here's the learning rate. Instead of getting predictions by simply adding up the predictions from each component model, we can multiply the predictions from each model by a small number known as the learning rate before adding them in. I don't know what that means. Honestly, I don't know what that means, but let's keep going. This means each tree we add to the ensemble helps us less. I guess that's what that means. Anyway, so we can set a higher value for in estimators without overfitting. If we use early stopping, the appropriate number of trees will be determined automatically. Honestly, I have no idea. And it is what it is. It is what it is. Like I said, we're at advanced learning. They are going to hang us out to dry. At least we have Gemini to ask what this is talking about later, not right now. In general, a small learning rate and large number of estimators will yield more accurate XGBoost models. Okay. Pardon me. Though it will also take the model longer to train since it does more iterations through the cycle. So as default, XGBoost sets learning rate to 0.1. Yes, okay. Modifying the example above to change the learning rate yields the following code, right? So instead of doing 0.1, all right, so first we changed the n estimators to 1,000, and we're also having 0.05 instead of 0.1. So we're having the learning rate, which was already pretty small to begin with. And then this stuff's the same. This will go up here, like I said, and verbose equals false. We're going to have to inquire from Gemini later. Not right now, because look, I don't know what it means, and I don't want to know. I just want to get us through this right now. We can query all this stuff later when we really need to get this. So we got in jobs right here. Nut jobs. No, just kidding. On larger data sets where runtime is a consideration, we can use parallelism to build our models faster. Oh, I don't know what that means either. I don't exactly know what it means, but it's going to tell us in a second. So it's common to set the parameter in jobs equal to the number of cores on our machine. Okay. All right. So I think based on this, I think parallelism means that we can set it to like I've got 4 cores on my processor. So we can make it like run all 4 cores and make the something run faster, right? So on smaller data sets, pardon me, this isn't going to help, all right, because it's already going to go fast anyway. So the resulting model won't be any better, so micro-optimizing for fitting time is typically nothing but a distraction. Okay, but it's useful in large data sets where we would otherwise spend a long time waiting during the fit command. So yeah, basically this is just going to make the fit run faster because it's going to use all 4 or all 2 of our cores, however many cores you got, to do this thing. And there we go. So here's the modified example. We've got my model equals XGB regressor. We've got the 1,000 on the n estimators. We've got the learning rates 0.05, and we also got in jobs is 4. All right. So now we're going to run it. We're going to do some parallelism. All right. As usual, this goes up here, and the rest is the same. So let's go down some more. So all right, this is a conclusion. Not now. So in conclusion, XGBoost. Let's click this. All right, we got the documentation page here for later. So XGBoost is a leading software library for working with standard tabular data, the type of data we store in Pandas data frames, as opposed to more exotic types of data like images and videos. Okay, I'm not worried about either of those. With careful parameter tuning, we can train highly accurate models. Sounds good to me. So now it's our turn. We're going to train our own model with XGBoost in the next exercise. Let's go. Oh, man. Yeah, this is just... Look, it is what it is, guys. It is what it is. At least we're here. We're farther than we would be if we were just trying to make this from nothing, right? So this is good. I think even though it feels like we're missing some stuff, at least we're here. At least we got Gemini. Anyway. Pardon me. All right. So now we're on to exercise XGBoost. And we'll see you next time.